I always find it easiest to think about what is the inner integral first. I think of the triple integral over the solid region R, say, of some function. In this case, all we were after was the volume of the solid, so the function is simple, just 1. But I am going to assign one center of mass problem due on Friday for a triple integral. So this could be a density function, delta of x, y, z, dv. If it were, for example, a density function in, for example, grams per cubic centimeters, this would be in cubic centimeters, giving you a quantity that's in grams. And the integral is just like adding. And so adding up all these tiny contributions to the mass gives you the total mass, is the intuition. But it doesn't tell you how to actually compute it. Think of it as a double integral of a single integral. The double integral being over some domain D in the plane. So R is representing the three-dimensional solid region. D is representing some two-dimensional domain in some plane of a single integral, where if you do the single integral inside here with respect to Z, then the solid does need to be described as being between two graphs of two functions of x and y. A lower function and an upper function. So then if you're given a picture like this, you need to see what those functions are. This solid is between this plane, this slanted plane that has equation z equals 2y. Notice it only depends on y, not an x. The output here depends on what y is, not x. If you cut it with planes this way, you get lines that are the same height, so it doesn't depend on x. And the bottom of the solid, which is z equals 0. So with respect to that ordering, it's from z 0 to 2y. But what about the double integral on the outside? Imagine compressing this solid onto the xy plane. Since the integral is with respect to z, compress it onto the plane that does not include z, the xy plane. Alternatively, you can think of it as a shadow projection. If you've got light rays coming straight down the z-axis, the shadow of this region is going to be, well, it's going to be the region that you see at the bottom there. That's going to be what D is. So draw a picture of that in an XY plane. By looking at this carefully, you can see the x-intercepts are at plus or minus 2, and the y-intercept is at positive 4. So a reasonably accurate picture is something like this. And that is a parabola. What parabola? It is this parabola, y equals 4 minus x squared, which makes sense if you look at its graph. Its y-intercept is 4, and its x-intercepts are plus or minus 2. So that is the region D, which then for the outer double integral, you think of either as vertically simple or horizontally simple. Sort of the more standard way is to think of it as vertically simple, which means it's between the graphs of two functions of x. Which means the outer dA needs to be dy dx. It's the sort of like the opposite of what you would think. X goes between -2 and 2. For each such value of x between -2 and 2, y goes between 0, right? Because that points on the x-axis. And this graph, as a function of x, that's that. 0 to 4 minus x squared. Still keep the inner integral with respect to z the same. So there's one ordering. And that was the ordering to actually do the integral for when it was a 1 here for the problem 14. Integrate 1 with respect to z gives you z. Going from 2y, 0 to 2y, you end up with integrating 2y from 0 to 4 minus x squared. It's not too difficult of an integral to do in the end, if this function is 1. If this delta function is not 1, then it certainly could be complicated. With respect to making this dx dy instead of dy dx, again, the inner integral is still the same, because that's still with respect to z. Look at the picture again. Y goes from 0 to 4. That's the outer integral. For each such value of y between 0 and 4, x goes between these extremes, that negative value and that positive value, two separate functions of y. You solve that equation for x. Get x is plus or minus square root of 4 minus y. And those become your limits of integration. Negative square root of 4 minus y to positive square root of 4 minus y. It's not clear that these are going to give the same answer. Or the other 4, and I will do at least one of the other 4 here. But they do, and it doesn't matter what delta is. They'll give the same answer. Though that doesn't mean the integrals are easy to do, depending on what delta is. Just for the sake of illustration, I'm going to pick delta to be z squared. I think on your problem due on Friday, delta is going to be y squared. Z squared. So this is a new example. It's the same solid, but delta is not going to be 1. It's going to be z squared. If I pretend the units of delta are grams per cubic centimeter, then doing the integral does give the mass. Let's just confirm that both integrals give the same answer. Negative 2 to 2. 0 to 4 minus x squared. 0 to 2y. Delta of x, y, z. dz, dy, dx. The mass is why is there a capital Y? Oh, because there's a capital Y here. About 277.4. Check that the other double integral gives the same answer. It should. It technically should give the same answer even if you can't actually do it by hand. As you've seen before, sometimes one integral is easy to do and the other one's impossible. Theoretically, they give the same answer. Switch around the dx and the dy. Mathematica took longer to do that and is getting a different answer. Okay, thank you. Thank you. Hopefully that takes care of it. Yes. Again, I will do one more ordering. But let's also talk about moment and center of mass here. If I was after z bar, the center of mass, third coordinate in the z direction, the vertical direction here, I would also want to find the moment relative to the xy plane, m xy, for this three-dimensional solid R, you'd integrate z times delta of xyz. And then z bar, the center of mass, third coordinate, would be mxy divided by m. We just found m to be 277.4. mxy, let's check it with both orderings. I need to multiply by z. 1210.48. Check it with this one too. 1210.48. So again, it doesn't matter what the function is. You get the same answer if you set up the integrals correctly. As far as the center of mass goes, so the moment is the 1210.48. The mass itself is 277.401. Z bar would be 4.36. The third coordinate of the center of mass of this thing with respect to the density function that I use, z squared, would be whatever I got, 4.36. A little higher than 4, halfway between 0 and 8. Higher, even though sort of the bulk of the mass is lower, it seems, probably because that density function being z squared gets so large once z gets higher. Is probably the reason for that. Even though the bulk of the mass is for low values of z, it's less dense down there. Much denser up here because, again, the density is z squared. And that density up here is winning out, so to speak, to make z bar higher than 4. Let's try one more ordering. I think the trickiest one is where the inner integrals with respect to y. If the inner integrals with respect to y, I want to think of the solid if I can. It's not always possible, by the way. I'm saying if I can. It's not always possible. But if I can, I want to think of it as a solid between the graphs of two functions of the other two variables, x and z. So I look at my picture and say, okay, here's my xz plane over here on the left. Can I think of that solid as being between two graphs of functions of x and z? Yes, it's between the slanted plane again. That would be the lower limit of integration with respect to y. And this curved side that's above it in the y direction. The slanted plane as a function of x and z is, solve that for y equals z over 2. It doesn't really depend on x. Y equals z over 2. This curved thing depends on x, but not z. It's y equals 4 minus x squared. So this is going to be z over 2 to 4 minus x squared. But what is d now? Draw it in an xz plane, since the inner integrals with respect to y. Compress this object onto the xz plane, or alternatively, imagine light rays making it cast a shadow on the xz plane. It'll be a parabola-like shadow. Since the highest value of z there is 8, the highest value of z here will also be 8. And x goes between -2 and 2. It's going to be a bit more of an extreme parabola. I'm not really drawing it that way, but that'll be an 8 up there instead of a 4. Still -2 to 2. You can just look at that and figure out its equation. Z equals 8 minus, not x squared, but 2x squared. Double check the x-intercepts. Is there a way to figure it out without just looking at it? Yeah, effectively, this slanted curve, this slanted parabola, is the set of points that satisfies both of these equations. And if you take this equation, y equals 4 minus x squared, and substitute it into this equation, y equals 4 minus x squared, getting substituted into the equation z equals 2y in place of y, you get this, which is the equation of that parabola. Along this curve, both of these equations are satisfied, which means z does equal 8 minus 2x squared. And by ignoring the y, effectively, I'm looking at the shadow of that on the xz plane. So the most natural way to do the outer two integrals would be to let x go from -2 to 2 and y go from 0 to 8 minus 2x squared. Same inner integral. dy, and then here The outer integral is with respect to x, so it's dz dx. And let's just go ahead and integrate. Let's find the moment in the z direction that way. It works for any function. So I'm changing this to an 8 minus 2x squared. This to a z over 2. This to a 4 minus x squared. Get the order right, though. It's dy, dz, dx. Okay. So this should give the moment in the z direction, moment with respect to the xy plane. This should be the 1210.48. How hard is the integral to do? It's hard to tell without looking at it. I mean, maybe this one might be the hardest one to do because of those square roots there. I mean, you could do the inner integral and see what you get, and then ask, would such an integral be easy to do with respect to x, going from the here to here? No, because you don't see an x here. You could also do the two inner integrals and ask if that would be easy to do with respect to y or not. Yeah, that does look difficult. I'm not sure offhand how to do that integral. Antiderivative. It might be a non-elementary function. Yeah, or just a really complicated function. You wouldn't want to do that one by hand.